Fantastic. Well, look, it's wonderful to be here amongst such a distinguished crowd, and I was actually impressed by the speakers we just had because it set a little bit of the scene of what I'm going to talk about today, which is not necessarily about how we achieve carbon neutrality, but certainly how we can adapt some of our key sectors for a changing climate. So I'm going to be talking about one of the ways that we can use technology to address some of the key challenges that climate change presents the international community, particularly around the aspects of food and water security. So firstly, I'd like to introduce myself, I guess. I'm Matthew McCabe. I'm a professor of remote sensing and water security at the King Abdullah University of Science and Technology in Saudi Arabia, so just on the other side of the Red Sea. So I'm going to present some case studies that we've been working on within the region, and while some of them are local in application, the goal of this work is really global in scale. So we're really looking at technologies that enable us to take local information to the planetary scale, and the principal mechanism for doing that is going to be the use of satellite remote sensing data. So I'm going to talk a little bit about that as well. I'd like to recognise the Prince Sultan bin Abdulaziz International Prize for Water. They extended the kind invitation to here, and I'm very happy to be joined by my colleagues at the audience. So like many of you, I'm sure you're motivated by a similar problem. 10 billion people by 2050, that's an extra 2 billion mouths to feed. Various estimates indicate that we're going to have to increase food production from anywhere to 50 to 100% at current levels. So that presents some real challenges, obvious challenges, even excluding the impacts that climate change are going to have on that, on finding a solution to that problem. Now, one of the key elements I want to take away from that 10 billion person challenge is that it's not a problem for 2050. We don't have 30 years to solve this. It's a problem of today. You know, we have 800 million people already who are under-resourced when it comes to the food that they require to eat. 1 in 5 children are malnourished, you know, through micronutrient deficiency. So this is not a problem that we can address at our leisure. It's a problem that has immediate concern, and we need to address it now. Now, in the face of climate changes, those problems are going to become even more challenging. And one of the ways that we need to address that is to flip the paradigm that we currently operate on, which is certainly not doing more with less. You know, the current paradigm is doing more with more. Now, we use more nutrients, more water, more land. That's unsustainable. So the approach that we need to investigate is this sustainable intensification of our agricultural systems. And one way to do that, there are a number of approaches that have been proposed, is use information to help us manage the agricultural systems which provide the food that we're using to feed a increasing global population. So tapping and mining new information sources is going to be absolutely key, and that's what I'm going to be focusing on today. Now, this is something that we've been working on for many years now, and I've talked about a local example, and I wanted to show this one as a case study. What you can see at the top is a 30-year history of agricultural development in one small region of Saudi Arabia, which has gone from nothing to a very dense agricultural development. Now, corresponding with that agricultural increase, which is principally being brought about to feed a growing population of the past, you see a corresponding decline in the water that's resource that's been provided to the kingdom through natural resources, but which is a finite natural resource. So there's been a decline of that groundwater reserve, and it's not being replenished. Now, although this is a local problem, it's a problem that's being played out all over the world. Wherever there's agricultural development, we're seeing declines of groundwater resources because they're being used in unsustainable ways. So we need data to help us manage not only the water resources, but how we are using that to grow the food that we need. Now, for a sector that's plays such an important role in the global economy, 1.3 billion people are employed in the agricultural sector. It's a $2.4 trillion industry. This is not a small backyard operation, but it's one that operates still very much in the dark ages. In Silicon Valley parlance, it's a sector that's ripe for disruption. Now, when you factor in some of the climate elements of this. It's, you know, number one contributor to landfill, principally because of the vast quantities of food that we waste. Now, there's a really sobering statistic I talked about before, a 50% increase in food production, current levels, to feed a 2050 population. Some estimates indicate we're actually already producing the amount of food that we need for the future. We're just wasting 30 to 50% of it. All of that's ending up in the landfill. So we need to arrest that waste for a start. It's the number one water user. 70% of all fresh water goes to the production of the food that we eat. It's the second largest producer of greenhouse gases. So these are all really major areas of activity that we need to address if we're going to solve some of the great challenges moving forward. And one of the things that I propose that we need is local knowledge at the planetary scale. We need to understand what is happening at the field scale, at the smallholder farm level, but begin doing that everywhere. And that's a message that I'm going to repeat throughout this talk. Now, this is just one infographic of a little bit of the landscape of Earth observations that we can take advantage of. This is a collection of European Space Agency satellites, past, present and future, but it gives you an idea of the vast resources that are available for Earth observation, and using that information, how we can then translate it into actionable intelligence, how we can actually turn that into something that can have a meaningful impact at the ground. Now, we're using government space agency systems, things from ESA, from NASA, from other countries as well, but the revolution in commercial sensing is something that's really been driving innovation in the space sector, and I'm going to focus a little bit on that in the coming slides. Now, just to go back a step and give you an example of agricultural activity and development, this is just two regions in Saudi Arabia over a 30-year record that we've been able to assemble because we have a history, we have an archive of Earth observation. So you can see these two areas alone represent about a third of the agricultural land in Saudi Arabia. You can go and count those pivots, which we actually have done. There's about 10,000 of them. And each of those pivots is using an Olympic-sized swimming pool of water every day. And that water is not being replaced. It's being depleted from the subsurface. There's no rainfall, there's no active rivers in the systems. And that's a pattern that's being played out in many regions of the world, particularly in this region. So we can take that information and we can start to develop knowledge. We can start to develop insights from that Earth observation data that can be used by individual farm holders, but in this case, government agencies. For many years, we've been working with the Saudi Arabian Ministry of Environment, Water and Agriculture to help them undertake something that you would think you would know: how much water you're using to grow the food that we produce. Now, it probably surprised you to know that this is not just a Saudi Arabia specific problem. Pretty much no country in the world has a good handle on how much water they're using to grow the food, let alone how much their groundwaters are declining or their freshwaters are being overexploited. This is what I was referring to about agriculture being a sector ripe for disruption. It's information poor, but by exploiting the advances in Earth observations, it's becoming increasingly data rich. Now, the job here is to turn that data into knowledge. And again, with that temporal history of archived Earth information that we've been collecting for decades. You know, it's Landsat satellite, for instance, we've celebrated its 50-year anniversary recently. So we have 50 years of Earth observation that we yet haven't fully leveraged to direct to some of the climate responses that we need to address going forward. But you can look back in time and you can actually see from this instance examples where government levers on the removal of subsidies, on policies to address or arrest overexploitation of water can actually have a demonstrable effect, and you can observe that. You can see the change in action. And it's this type of information that we need to bring to bear for climate action as well, so we can see and observe the change as it's occurring. Now, a few years ago, I'm an academic, we wrote kind of a forward-looking synthesis of what the future of Earth observation might look like. And being an academic, it probably wasn't very forward-looking. It was probably about a year or two out of date, because the future had actually already caught up with what we were writing about. But two things that we had identified as being disruptors was the advance of CubeSats, and I'll explain what they are very shortly for those who may not know, and also UAVs. Now, for CubeSats, the traditional approach for Earth observations has been for space agencies to launch a single satellite, a big SUV type system worth about $1 billion. And that worked pretty well for research applications, but it wasn't a very good commercial model. You don't want to put all of your infrastructure and technology into one platform. So the commercial approach, particularly led by companies exploiting CubeSats like Planet, has been to flip that on its end. Instead of investing in one single satellite, you invest in 100 that are 100 times cheaper than $1 billion or a scale therein. And you can launch these satellites into space, and that provides a very nice answer to a challenge that faced the Earth observation community for the longest time. And put simply, up until about 5 years ago, you had a choice. You could either see something in high resolution occasionally, or see something regularly, but with poor detail. So it was a resolution and repetition problem. Planet CubeSats came along, they've launched hundreds of these. You no longer have to make that compromise anymore. You can see high resolution frequently. And what that allows you to do is start to get the type of information we need to make decisions on the ground. So here's a little example of the type of satellite systems that are available and their timescales. And what we're dealing with now is these CubeSats in the corner, which provide very high resolution information, 3-meter data, anywhere in the world, at daily scale, or in some cases better. And with that information, we can start to do things of interest and importance to the agricultural sector. We can start to map the crop health and condition, smallholder crop health and condition in some cases. Now, these are big fields. These are about 500 metres in diameter, but you can start to see changes within the field at a daily scale. You can see the crop development and crop health. You can identify areas within the field that need remediation or remedial action, whether they're being underwater or under-fertilised, or if there's a disease or pest infestation. The farmer can take action on the ground with real-time information. And then you can extend that to try and predict how much water is being used. That's where we come from as a key element of the work that we're doing in our group. How much water is actually being used? Where can it be used more effectively? Trying to answer the more crop per drop approach. So this is my last slide, and it's really just going to overview what we've been hearing about already. If there's one take-home message in all of this, is that climate change is going to amplify many of the problems that this sector is already facing. And when we talk about when we talk about food security into the future, you basically, it's the same equation. Water security is equal to food security. You can't have one with the other. Now, when we talk about feeding the next 2 billion people, many of which are coming in the developing world, the challenges of providing that water secure and food secure future are immediate. The answers to that question need to be provided now so that we can plan for the future. High-resolution Earth observation is going to be a pathway to providing those solutions. But there are still challenges, there's roadblocks, there's massive data volumes. So how do we make this data accessible to the people that need it? How do we turn that data into information that people can use? And it comes back down to the very basic business maxim. You cannot manage what you do not measure. And we really need tools to monitor every field, everywhere, all the time. Thank you.